All right, well, almost done. But let's recall back from chapter 10, we had some fun with the hyperbolic motion, and we'll revisit that here. So we have A, does a particle in hyperbolic motion, equation 10.52, radiate? Use the exact formula, 1175, to calculate the power radiated. B, does the particle in hyperbolic motion experience radiation reaction? Use the exact formula, problem 33, to determine the radiation reaction force. Okay. So, part A, the power radiated comes from, where's my mouse? Comes from P equal mu naught Q squared A squared gamma to the sixth, 6 pi over C. Hyperbolic motion, we were given the W function, so that's B squared, closest approach, plus C squared T squared. Okay. So with that, we have V is equal to the time derivative of W. So take that derivative. Be careful simplifying. A is just equal to V dot. So take the derivative again. See, we get a quotient rule hidden as a product rule. Easy enough. Again, find common denominator, cancel away, and we see what the acceleration is. Gamma squared, we know what that is from all the other substitutions. So we just have 1 over 1 minus V squared over C squared, so plug the V in, cancel away, reduce away, find a common denominator in that fraction, in the denominator, And then we know that when we divide by a fraction, we multiply by the reciprocal, so flip it, and we can cancel away the common factors in the new denominator, and we're left with gamma squared equal B squared plus C squared, T squared over B squared. So not as bad as it could be, actually. With that, we have A squared and gamma to the sixth, which we could write as gamma squared cubed. So that's where our two parentheses terms come in. And now it's just a matter of simplifying. I mean, this one really isn't that bad, but these terms need to cancel down accordingly. Again, we use that C squared to bring in an epsilon naught and mu naught. And so we'll cancel the mu's. And we see that we end up with a Q squared C over 6 pi epsilon naught B squared. So yes, it does radiate. In fact, at a constant rate. We don't have any velocity terms there. We don't have any acceleration terms, so we're good to go. Now for part B, the F radiation, we now know that the expanded version of the Lamar formula has A dot plus 3 VA squared gamma squared over C squared. So we know what acceleration was last time. Now we'd have to find the derivative of the acceleration, which is given as such, and we tidy it up accordingly after we, of course, substitute and cancel whatever terms we can. So then the parentheses term goes to A dot plus that 3 fraction, and we can actually simplify that down. So we get A dot plus 3 over C squared times A squared, times A squared, it should be squared. And then gamma, V and A squared, and then times gamma squared. So we have the 3 parentheses on the bottom. And ironically, or maybe not ironically, but convincingly, that all multiplies down and cancels to 0. So A dot is equal to that 3 fraction, or the negative 3 of that fraction. That's pretty cool. The force radiation, the radiation reaction is 0. How cool.